All right, what could possibly go wrong in a 5-stage in-order pipeline? What if this NAND was, let's say 3, 4, 5? What would happen?
Well, because the ad's using the 3.
The ad is not using the 3. Well, it's using it. It's well, what is it? It's writing to the 3. But does the NAND have that proper value?
No.
Why not?
Because it hasn't finished yet.
It hasn't been computed. So that is. Do you see that problem?
Mm-hmm.
So that's called a data hazard because it doesn't have the correct data. All right. What's another issue that could happen?
With that same example.
No, I didn't put it in here.
Well,
What circuit did I talk about many times but never actually used?
the DC plus offset.
Yeah. So what if we needed to take the branch? If we need to take, let's say that this was the branch right here and it says, oh wait, you need to take this over here. What about these 3 instructions? What needs to happen to them?
Need to be erased.
They need to be erased. So that is called a control hazard because your control path is not correct. All right, y'all see that? Data hazard and control hazard are the 2 things.
So your branch gets loaded and it keeps moving along and everything behind it just keeps getting loaded
Right.
until it executes that branch that says, whoa.
Whoa, wait a minute. Whoa, we've been doing the wrong thing the whole time.
So
And then
that's
it's,
one drawback of pipelining.
yeah. The big drawback to pipelining is that, yeah, if you need to branch, you're now going to have to flush your pipeline.
So therefore, you're talking about branch forecasting,
Or prediction.
prediction, yeah. And that's, I assume, going to help somehow when we get to that.
Yep. So that's control hazards, how you fix that. How could you fix the data hazard? And that's this example. We'll go back to the data hazard. Let's say that the NAND is using the, let's say it just says 3, 4, 6. How could the NAND use the 3 right here? Well, here's a question. Where is that 3 stored? At this moment.
At this moment.
Yeah.
That's a good question.
It's in the data it's in one of those.
It's over here,
Yeah.
right? But so really, you just need to take this and shove it. You need to move it over here, right?
Yeah.
So that's called data forwarding. So branch prediction is going to help with you not having to install. Data forwarding is going to actually avoid the issue altogether by just forwarding the data along. Because you do actually have the data, you just need to move it to the correct location. That's called data forwarding.
Yeah.
All right. So data hazards, that's what I just talked about. One instruction just needs the, that NAND needs the 3 after the add. Control hazards, what if you actually do need a branch? The last one's called exceptions. So an exception or a trap is, let's say your program all of a sudden needs to execute in kernel mode, so it throws an exception so the processor stops and start executing from the kernel. What would you have to do in that case?
Nukes.
Yeah, nukes. You have to no-op everything, get the new PC counter in there, and then start executing again. That's just how you have to do it. All right, so data hazards, what are they, and how do we detect them? So, for example, we're going to talk about data hazards now. Sorry, talking about data hazards. We're going to talk about what are they, how do you detect them, and then how do you deal with them. Okay. So when do they happen? Well, decode needs to read the source operands from the register file, but the sum may not be written until write back. So there's this time problem. That's a pipeline for add. Looking at it pictorially, here's that add and NAND I was just talking about. The 3 is not written back until write back, but NAND needs it at decode, which happens here. So I guess one solution would put time machines in every processor, but have you made that yet for us? Oh, man.
Unfortunately, it's not OS either, so we can't just cache it or ignore it.
Oh, yeah, we can't. Yeah. Yeah, you definitely can't ignore things in architecture. That's not acceptable. All right. So if we're not careful, NAND will read the wrong value. So we need to somehow forward it. It looks like we need to go into the future, but luckily we don't. So if we look right here, oops, we can first detect if the register is going to be used by just storing what the destination register is of each of the forward proceeding pipeline register files. So each of these destinations are going to be stored over here to detect if there is a hazard. Okay? This is how you detect them.
Okay, I see.
And we're going to have some forwarding logic right there. Hopefully that'll make sense in a moment. Okay. So once you detect them, whoops, what are different ways to fix this issue with data hazards? There's actually three standard ways to do it. In operating systems, we would ignore it. Terrible solution. What can we do? After we detect it, what can we do? There's two things we could do. I've said them both, but let's make sure it's clear what those two are. We've detected there's a hazard, namely that, let's say, register B is not going to have the right value because it's part of the destination register up here. What could we do?
Forward it to it.
So one is to forward it. The other is to stall until that hazard no longer exists. So you can either forward it or stall it. Which of those is easier to implement?
Stalling.
Stalling, right. Which one does your lab ask you to do?
Probably forwarding.
Yeah, you got it. All right. So we could avoid, make sure there are no hazards in the code. Going to be a terrible solution. Detect and stall. If a hazard exists, stall the processor until they go away. Well, our code still works, so that's fine. Detect and forward. If hazards exist, fix up the pipeline and get the correct value if possible. There's actually one instance where it's not possible here. So avoid. Assume the programmer or compiler knows the processor implementation, aka you know that it's a 5-stage pipeline, so you just put no ops in between this add and this NAND, and that gets rid of the hazard, right? Because by the time this instruction executes, you have the value. Right?
Yeah.
Sounds great. What's the
That
problem
would
with
be your
doing this?
compiler, right?
What?
Your compiler would do that.
Yes. Why is this a terrible idea?
Doesn't it depend on the machine?
Because now your performance is going back down.
Okay, there's a performance issue. But what does that mean you have to do with all your old programs when you install a new processor?
Recompile.
You'd have to recompile them. Are people willing to do that?
Nope.
Well said, Matt.
Thank you.
So, old programs are not going to run correctly. Longer pipelines need more no ops. Programs get larger as no ops are included, which already makes the memory problem even worse. Intel EPIC, which actually tried to solve. It was an EPIC. What the EPIC did is you didn't, instead of instructions, you had bundles. So each bundle was 4 instructions that the compiler told you can all be executed in parallel. You didn't have to worry about data hazards. And when they did that, they found out that 25 to 40% of the instructions inside these bundles were no ops. So, I guess it wasn't that great of an idea anyways. Therefore, program execution is slower. CPI still approaches 1, right? But now you have all these no ops. All right. So, like I said, is this a good solution?
No.
No. Terrible solution. Detect and stall until ready. Okay. Once you detect it, keep stalling until it goes away. And just pass along no ops. All right. So once you detect something, how do we detect it? Well, inside this hazard detection unit, notice that these 3 are holding the destination registers of the forward of the proceeding instructions, and these are the 2 registers. So if we zoom in a little, again, these are the 3 proceeding registers that we are going to write to. We would have simply a comparator between those and each of these register lines that would detect the hazard. which is basically just a bunch of XORs into a simple NOR at the end that tells us if we have a hazard or not.
Mm-hmm.
It's been a long time since I've seen this.
It's like,
The hardware, I mean.
oh yeah. When you said that, I really wanted you to have, the Jedi costume on, lightsaber. That would have been beautiful at that moment. All right. Keep the instruction in fetch and decode, pass a no-op until it's ready. So you'd have to add basically an enable bit to your fetch as well as your PC. And basically the hazard detection unit would just disable these two, which means that nothing gets written to your IFID pipeline register or your PC counter. So it just keeps doing the same thing over and over again, which is just fine. And then pass a no-op to execute. So it keeps passing no-ops, hazard, pass a no-op, hazard, and then finally we're done. So then we can continue the next instruction. Okay. Make sense? Perfect sense?
Yeah.
Good. So what does this look like? Well, hold on. Actually, yeah, what does it look like right now? Well, you have fetch, decode, execute, memory, write back, fetch, decode, 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 execute. What's the issue here?
You need 3.
Well, what's the issue performance-wise? Your performance goes down.
Oh, yeah.
So CPI increases every time a hazard is detected. Is that necessary? I put the answer for you.
No.
Not always. No, I didn't say no. I said not always.
Tricky.
Tricky, a little different. You can reroute the results. So a NAND no longer needs to read from register 3. It can read from what's later. This lets us to complete the decode cycle and move it forward. But now we need more control to remember that the data we aren't getting from the register file at this time will be found elsewhere in the pipeline in a later cycle. Does that sound like fun?
Oh, yeah.
Lots of fun.
Lots of fun. Oh,
The hardware is going to be just, to me, just as simple as doing the detection and install.
Oh, yeah, detect and install is way easier than detect and forward. But I'm asking y'all to do detect and forward in the homework, so this is what you got to do.
Right.
Okay. Detect, same as detect install, except all 4 hazards are now treated differently. So you can't logically OR the 4 hazards, and I'll show why in a minute. You can bypass the data route to where it is needed, and you'll need some more muxes. Beware, stalling may still be required even in the presence of full forwarding. And we'll get to, actually, can you think of the example for that?
Every instruction is trying to use the same register, I guess.
And here it is. Ignore the in cycle 4. All right, look at this. When would you still have to stall? There's one instruction where you have to stall. All the other ones you can forward. So like an add after, an add after an add, you can still forward there.
Add right after the load from
Right.
the memory.
Yeah, because the memory has to take this in cycle while it adds and execute. It can't, you can't pull it from memory in the future, so you have to wait one cycle on a load word when there's an instruction right afterward needs it. That's the only time you're going to have to stall. So make sure you test for that as well.
Wink, wink.
Wink, wink, nudge, nudge. Say no. All right. What hazards do you see in this code?
The add and the NAND.
Mm-hmm. There's another one.
Yeah, there is.
The first add and the first NAND. The
The
first
two
add.
adds with the 7.
Hold on. The first add actually generates 2 data hazards. The add and the NAND, and what else?
Oh, the second add.
Right. The second add's using it. It hasn't been written back yet. So you got to forward. Remember, you now need to forward between multiple possible pipeline registers. It doesn't hazard. Excuse me. There's no hazard here because it's finally been written back. Now go ahead with your 7s. Yeah, there might be might be some issues here with when they're writing back, but not in this case. Luckily with in
Yeah.
order, it retires in the order it comes in, so that's okay. Wait, are there any more?
Okay, so stupid
Oh.
question.
Yeah.
I'm still trying to get the order of my assembly. So you're adding
1, 2 into 3,
into
3, 4 into 5, 4,
3 into
7. And remember, it's contents of register 6, contents of register 3 into 7. And you're loading base 3 plus 10, register 3 plus 10 into 6,
Into 6.
register 6 plus 12 into 2.
So that's fine. That should be fine.
No, because you got to add, or I'm sorry, to the store word, you got to get the value of 6 first, which you haven't yet because of the load.
Load where it's loading from 6, isn't it?
It's loading from 3 plus 10 into register 6.
Oh, okay.
So then now you need to calculate the address of contents of 6, which is loaded in the previous one, plus 12. All right. Now I'm trying to... Whoa, what just happened here? Okay. So this is the 1, 2, 3, and it's not showing me. Okay. Guys, that's what's going on. Here's the add. Add 1, 2, 3, and the NAND is right afterwards. Add 1, 2, 3. NAND is right here. Hazards detected. NAND, add. Hazard still detected. That's why I would forward from that add straight back here.
So it's coming and then loading it into the MUX.
Yeah, so you need another MUX here signaling if there's a data hazard, and where do you read it from? Well, you're going to read it from the ALU result of the EXMEM stage.
What's the little signal going to the bottom MUX?
Well, you don't know if it needs to be the top MUX or the bottom MUX, right? Because if you're adding registers 1 and 2, which one are you adding it to?
Is this the complicated stuff for the first project?
Yes.
Okay.
Well, no. Well, yes. Yes and no. This is the first half of the complicated
Oh
stuff.
boy.
Yeah, wait till we get to the next
It's
one.
only half of it. So,
Yeah.
Right?
Yep. Oh, and by the way, you do need to have hazard signals to signify where, tell that MUX which value to get it from.
No.
Yes.
It's not
And,
the instructions.
oh, and then the NAND, now the NAND forwards to the add, if you recall from those previous instructions. Cycle 5.
Bottom there.
Oops. Oh, I lied. I'm sorry. Remember that second add had a hazard with the first add, right? So now you need to forward from this all the way up to that to execute. So now that's forwarding from a different stage. I'm such a liar. Again, you need to know what type of hazard it is so it knows where to load it from. No hazards. Let's see, we're going to do the load word. And remember, it's a load hazard. And since it's a load hazard, that means we need to stall for 1 cycle. So you're still going to disable the IFID pipeline registers and the PC counter so that a no up gets passed through for that one. And then the store word can go, because by the time the store word, what's wrong?
I just saw his head blow off, that's all.
Oh, his?
Yeah. Mine's right behind.
So when the store word comes in, right, you can at least grab it from the load word and calculate the correct address. Okay.
So yeah, can we go through that about 10 more times?
All right, let me stop the video and I'll just play it on loop. All right. Let me go ahead and pause the video. Actually, we'll go back up. Which part doesn't make sense? All right. Maybe it'll help if I wrote those on the board.
Yeah.
Well, that's the great thing about having it on video. You can go through it 10 more times.
Yeah, you just code through it 10 more times.
But not that part.
Just write that to a different screen. Okay. That add, right?
Right.
We've detected a hazard for register 3 with the next NAND.
Yeah.
Right?
So you're detecting it as soon as you load it in there.
In decode. Decode has to detect it. Because decode is the only stage where you're going to stall, where you can issue the stalls.
So, go back to the very beginning of it? Or
This is the beginning.
Okay, so 3 already went through or whatever, right?
Yeah.
So like add 1, 2, 3 went through, so you stored the 3 because that's the register you're going to.
That's
That
being
will serve
written
it.
to.
Yes.
Yeah.
And then your IFID thing or whatever, or in between there, you saw that the NAND has 3, 4, 5, and you saw the 3's there and the 3's there, so there's going to be a hazard.
Correct.
Okay.
But since we're doing data forwarding, and this isn't a hazard based on a load word, you are able to fix it.
Right.
All right. So, hazard 1, and we'll just say that that signals that you need to pull from the ALU back around. Notice the add is being written or fetched. There's a hazard with, okay, I don't know why the 5 is there, so this instruction and that instruction are different. Or something. What's this 5 doing here?
5 is.
Oh, 5 is what's being written right here. Never mind. I got it. Never mind. The 5 is because that's what.
Yes.
Yeah.
Whew, man.
Amateur.
That was close. Whew. All right. And then the NAND, since the NAND is an execute, it's going to be forwarded from the ALU result of the proceeding instruction. Back up here, it knows to select that mux because of the type of hazard it is. So you need to write your bits for your hazard down here. Does that make sense?
So the different types of hazards have different ones,
Mhm.
and that tells you. Okay. And I'm assuming there's a list of these things somewhere.
Nope.
So
Really?
H1 and H2 is this.
I'm just calling them hazard 1, hazard 2. It's not just one piece of information here. It's multiple, because you need to know which mux are you selecting from and which pipeline register are you taking it from.
This pipeline register is the register file.
Right. These vertical bars are the pipeline registers. This guy is the register file. All right. Any other questions on this one?
Not yet.
So that's just to tell you that the hazard is selecting from that mux. All right, next instruction. So here's that load word. And the add, which is in execute, is there a hazard we need to fix? Oh, we're going to do something else first? No. So the hazard that needs to be fixed is we need to forward from the top add over to this add. That top add is in the write back stage, so you need to forward from that mux over here, not just to the register file, but to this mux on this ALU as well.
So it's got to go into both of them.
Yep.
But the other hazard didn't need to go back to the register. It went just.
No, because remember this one's in the write back stage, so that's when it's actually being written back to the register file.
So where's that first add at right now? Add 1, 2, 3.
It's over here.
Right.
Okay, and that needs to be forwarded where?
To the execute for this add right there.
Okay. Okay.
But it's still being written back to the register file. in
Because
all
that's
three.
what it's supposed to do during write back. So it's doing all
That's
the
normal,
write back operation.
but we're pulling it out and also putting it in the mux.
Right. Because we
next
couldn't pull
add.
it out earlier because it hadn't been written back yet. So we put it here.
And the reason we're pulling it out is because the add has already gone past.
The decode. How's it going, Matt?
Pretty good.
All right.
Moment.
What's wrong with load word? Oh, wait, no, we don't have a problem with load word. Great. So that's the hazard. We just called it hazard 2 in this example. No hazards yet with the load word.
Yeah.
Yet.
Well, you missed an ad, didn't you?
Yeah, I did. There we go.
It's operating system.
How's that? What do we do? So now we have the store word. Remember that NAND is going to commit the 5 back, commit from the values of 3 and 4 back to 5. Do we have a problem with the store word?
No.
Is there a data hazard with the store word? 6, let's see, 6 and 2.
Yes.
Yes, from the load. Can we fix it?
We can install it.
Can we fix it with forwarding? No. We could fix it only with, there's a
You're loading it into 6, so you have to get it out of the memory, which
Right.
is in the next to last cycle.
Right, because it's in too far in the future. So it's a load hazard, so we're going to disable the IFID pipeline registers and the PC so that they do not increment correctly. Excuse me. Then pass a no-op as well. So we have a no-op here. You have your load word is going to be executing data memory. That last add will finally be written back.
So what's the program counter going to do during that time? Is it just going to stay the same?
Yes, the program counter is going to stay the same. All right, and now we have no op in the pipeline. Look down here at the bottom where I had load word add NAND, and now I have no op load word add. So I simply added a no op. I just issued a no op.
And then your store word is
And then the store word
in decode.
in decode still, that's correct. It's a hazard, but now can we fix the hazard with forwarding? Yes, we can fix it with forwarding now. So, since we can fix it with forwarding, we're going to go ahead and forward it. I'm going to issue it, sorry. So it's going to be store word, no op, load word. There it is, store word, no op, load word. Since we have the value of the load word, we need to forward it back to the MUX because we have a different, our load word data hazard. And then that will be forwarded to this MUX as well as written back to the register file. All right. How was that?
Yes.
Better?
Yes.
All right. And then we finally retire the no op and the store word. All right, let me